Multiple different types, dipole free-form fluxes. And the supergravity folks have a trick for studying these called consistent truncation, where they write down the effective five-dimensional theory with this mode, and then solve it. And it's really magic because there's no symmetry that would prevent this. The bigger mode here is some harmonic on the sphere. It's not lower in energy than the other harmonic by a lot. Symmetry doesn't keep persisting with them, but there's some supergravity magic where they can write down the five-dimensional Lagrangian, solve it, and then lift it to a 10-dimensional solution, and it can be applied to this case. And so first, for the case of one massive flavor, when they do this, they get a five-dimensional potential that looks like something like this. Dealing with this up here, which seems kind of unmoving, but as we discussed, this mode has negative mass squared, but if it's not too negative, then the boundary conditions stabilize the system a la Wright-Lorenz Friedman, and it's okay to have the super. And we know we're in this situation because if you go back to the m squared equals delta minus d dictionary, being relevant, that is delta less than d, exactly means being tachyonic in the supergravity, and you kind of guess what happened. There's some solution where the field rolls, so here's the value of the boundary, here's the value of the horizon, and there's some solution which has here's z equals 0, here's z equals infinity, here's ADS region. There's some transition region as you roll down the potential, and then there's a new ADS solution. So this is a particular. This is exactly what the field theory reasoning leads us to believe, that you flow from one strong coupling theory to a new strong coupling theory. You can match up the details of what you expect. Yes, sir. It's really the d value is satisfied here, meaning that there's no instability. Tom talked about this too. There is no instability in time. But there's in some sense, there's no instability. But you don't roll down anything in time because the radiant energy protects you. But you can roll down when you travel in space in the radial direction. That's what you're doing. Sir. If you see potential like this, you don't expect this to be stable. It's a solution. That's what I'm saying. And I'm saying that it is stable because I'm not sure the quick infinite is in question. But I'm saying that it is stable because there's also radiant. There's also radiant energy that if you look at the time evolution, actually, in terms of potential output. I'm saying it's dual gravity theory. What kind of stable? In dual gravity theory, you have this is the potential in the gravity theory. Sorry, this is the potential in the gravity theory. And when you look at the radial equation, there are solutions which start here and end up here. Now, with two masses, you can do the same thing, and there's some other direction in the potential that you're flowing in, and this one's different because you end up flowing sort of out to infinity in field space. With two masses, this same strategy, when you lift it to a 10-dimensional solution, gives you a singular solution. So this is with one mass. It does what you expect. Two masses gives you a singular steady solution. But it doesn't have advanced singularity because then you look at it carefully, you realize that it's just a bunch of D3 branes. And so what the geometry is here is that, well, let me draw ADS space, proper ADS space. This way, this is z equals 0 the boundary, and the spatial things are changing up. And it never gets to z equals 0. It brings the better way to the picture. But the point is that the whole space, see, watch you really draw these. The point is that you never get to z equals infinity. The geometry smoothly rounds off. This is actually not easy yet, but the contact direction here. And this is z equals 0, and they smoothly round off at some z equals z max. In terms of the metric, you have this ds squared is L squared over z squared, theta mu nu, dx nu, dx nu. And again, in the ADS geometry, one has arbitrary low energy excitations by moving the excitation to smaller and smaller z. That reduces its energy in terms of the gauge theory as much as you want. But once you cap off the geometry, you can't do that. And so you have a relative perturbation to the conformal theory. There's a good chance that all you're going to do is give mass to everything. And on the geometric side, that's reflected by capping off this geometry. Here, though, it works out that you've got this plus you have n minus 1 d3 branes. Not d3 branes, sorry. There's the minus 1 is distraction. We'll talk about that in degree. And so the bulk theory exhibits exactly the massless sector that you would expect from the field theory. And the thing about cyber witness is the whole moduli space, these D3 branes actually have lots of places they can sit. And it's true that when you bring them together in certain ways, you do get, as Tom reminded me, interacting fixed points. And actually, you would expect then on the gravity side to get some interesting geometry as you reach those points. And I remember thinking of this years ago in everybody. Do you know if anybody ever turned it out? Homer problem. Yeah, it's a great question. So part of the problem is that the supergravity folks first had to tell us what the metric is for arbitrary distributions of D3 branes, because this trick gives you special distributions. If they would tell us what arbitrary distributions, then we could bring it to the argument and find out what is the geometry. Also, a nice geometry picture of this is very important. You have to see something special that happens if you get for a margin. We don't just understand for yourself. Okay, right. Right, you said, we understand that for small network, where it might not be the geometry regime. Good. Okay, with three masses, you try again the same trick. That is, you get the potential, you follow it off. The 5-dimensional solution you get lists to a singular 10-dimensional solution. Question? Yes. A good question. This consistent truncation magic uses it because of the moduli space. And of course, it's actually what the moduli space is. the different conjugation is a solution generating grid that doesn't capture everything. And for a while, it was a goal to try to find the gravitational description of the general point on the moduli space. But it seems to be beyond the supergravity. You don't have to be there, but that's describing the direct reaction of the free grains. It seems like an open question. The first people have done the most of it for pulsing order, and they pushed on the problem, made some progress, but I don't think they ever gave a general solution. It's not smooth when the field went up to infinity. It's unique that it's a necessity. They look at the radical equation, and it's a trick. And it's a trick which is one-to-one with you now. So in fact, we have three masses. This becomes even starter because let me see what happens with three masses. With three masses, you can do the same thing. The five-dimensional thing flows off. You get a single ten-dimensional solution, but it's not any recognizable sensible brane. No, this is to be, so there's no 11D left. Yeah, well, again, the two masses are really just free branes. Let me finish this. How do you have the free masses? So free masses, if you're mass transfer, you look at the gauge theory side of the duality of respiration. If your superpotential is W is ML, then the volume mass is equal, say, phi alpha squared plus alpha beta gamma commutator of phi alpha with phi beta phi gamma is all traced. And I'm leaving off the constants, then the F-term equations tell you that, again, I'm leaving off the constants, n phi alpha is epsilon alpha beta gamma commutator of phi beta with phi gamma, which is to say that you have vacua, for any, so again, these are n by n matrices, and you have vacua for, so there is one vacuum for each n-dimensional representation of SU2, then it doesn't have to be reducible. So there's a huge number of vacua, including the trivial one, phi equals 0, and phi equals 0 actually is the confining one, and the other ones have various sort of mixed confining Coulomb behavior. But remember that the scalar parts of these superfields arose as the coordinates of the D3 branes, and this is saying those coordinates are becoming non-commutative, which comes back to the question from the last lecture, because Bob Myers explained that when you put D3 branes in a transverse flux, it's considered to be favorable for their coordinates to become non-commuting, and they pop out in two directions to become D5s. And so the correct behavior of the supergravity with free masses is it ends on, it actually ends on a D5, or an S5, or in fact, sums of many 5 branes. And the fact that there are many ways to calculate the geometry reflects the fact that the theory has many vacua. And so there's a nice match between you see the several things, there's a nice match between theory expectation and what the gravity tells you, but also it takes some trial and error in many cases to figure out where the geometry flows to. It's not always obvious. The perturbation gets big, and it's not obvious what the geometry does, and in particular, it's useful to have insight from the gauge theory as well. By the way, once one does this, one can go back and figure out what the consistent truncation was doing, and it was trying its best. It was producing some smeared version of the D5 brane. It was smearing this to the 5-dimensional object out into like a 6 or 7-dimensional object, and so it was trying very hard to get the right answer. Okay. Now, the last thing I want to say about, I'm pretty much on schedule. The last thing I want to say about this is, I told you that one of these theories confines, and I want to tell you how to see that. So, one of the things I talk about is to measure the potential between a source of a organ, like we're fundamental, that maps, so the QQR potential. Fundamental. There are always fundamental sources. So here is your boundary, and it corresponds. So the string, if you think about it in going back to Cust and Wilson, is thought to be the color electric flux tube. And what you could say more to justify this, the time is short. The way you calculate potential is to consider a string hanging down from the boundary, and then subject to suitable renormalizations, the potential is just the tension of that string. Yeah, the tension is the total energy of that string, I think was tension. Now, the tension, the effective tension, so again, this is the Z direction, is the local tension times the translation, the translation from local inertial coordinates to the global coordinates. And so the further it hangs down, the less its energy, the further it hangs. And in fact, in ADS phase, you get, as you must get, because just by the scale invariance of messing units, as you pull the ends further apart, the string hangs down lower, and so it can reduce energy and in such a way that the potential goes one of ours. The coefficient is interesting, but no time for that. In a confining vacuum, on the other hand, we have this idea that there is some Zmax. And so, the draw is a bit larger. The string hangs down, but it can only hang down as far as the space lets it, and then you pull the end further and further apart, and most of this thing is just running along the bottom of the space at the larger value of Z, or the value of Z you can get. And so the effective power of the string is just, it's on 0. It confines. And that's what happens with 3 masses. With 2 masses, the charges that you are not confining, they're coulombic, but for a different reason than over here. There is a floor to the space, as I was saying, for n equals 2, for the two masses, but there's also the D3 range. And so now I'm going to draw the same picture. So here's G equals 0, where the string hangs down from. Here's the floor, and now I'm looking from a different perspective so I can see, those D3, so I'm looking now from the perspective that sees the three directions more explicitly, and so here's your D3 range sitting at the bottom of the space, and the strings hang down. But once the string ends on a D3 range, it doesn't go, it stores its flux. But the flux is just a U1 gauge field, and it's free to spread within the D3 range. So you get a Coulomb potential for a different reason than you did in the AES space, but it's still Coulomb. So the general thing, D3 pursuit, just going to lower this law because all the arguments or ends on arguments. It doesn't just end, there's always some, the arrow from the other way, I guess. There's always some flux carried by these objects, which has to somehow run through the argumental object. But again, because the three range has a really gauge field, the flux is spread through it. Okay, so that's the general idea of RG flows and also some specifics. Yes. You've got strings, you have D strings, and you have PQ bound strings. So yeah, you have these sort of SL2Z multiple objects. So in fact, with all of these phases, you also want to ask about the touch loop, the status of the magnetic, essentially magnetic objects. Are they combined? Are they below mechanisms? There's always an analogous story for those. And similarly, you can ask for external dynamics loops. Now, some CFTs have operators in the range between the minimum allowed by sort of unitarity, by the Coulomb algebra, and half the dimension of the space of the CFT. And this is the regime where, as we said, you have to take the alternate boundary condition, the less obvious one, on the scalar field at Z equals 0. But this is also special for another reason. It's special because 2 delta is less than Z. And so the double trace operator squaring the original operator is relative. Now, again, I'm using here large N factorization. In the large N limit, the amplitudes for the two operators at a point, and they're each connected to the rest of the graph. But the leading N amplitudes are fully disconnected between the two operators, and so its dimension is just twice the original dimension. And so we want to see where this goes. And it's an interesting story. So, for a couple of reasons. So, let's perturb. So we have our generating functional for the original CFT, and now we're going to add to it a double phase perturbation. And the nice way to think about this is to introduce an auxiliary field. And so understanding where this theory goes to isn't going to be so hard because we can just use this trick to rewrite it in terms of the theory we know more about. The theory was just single phase operators turned on. And this is, in fact, just like the usual definition, integral d sigma, e to the minus 1 over 4g, integral, and then the usual t for j plus sigma. Just the generating functional for the single phase correlators. Okay, now we can now do the sigma integral in a large N limit. We can now do the sigma integral just by saddle point. We can just find its saddle point. And actually, what this probably is the right answer beyond large N, but let's keep things simple. So we just evaluate this by saddle point, and the saddle point is at 1 over 2g sigma. The saddle point is at 1 over 2g sigma equals partial z partial sigma, which the generating functional, so you're differentiating one with respect to the source, just pulls down the expectation value. And if we go back to our original dictionary, a given operator in the CFT is just the normalizable mode of the quantized mode of the quantum field of the bulk. And so this is alpha, the quantized mode, as a function of beta equals j plus sigma. The fixed mode is set to these values, and then you evaluate the quantized mode. And if we now plug in, rewrite what we have here is that 1 over 2g. Actually, there's what if I C sub O's here? Some constant. 1 over 2g. Beta minus j is equal to c sub O alpha. So what you see is that introducing double phase perturbation is equivalent to introducing a boundary condition of this form. And there's some process on here that aren't so interesting. And forget j for now, which is just again a source we're using to the generating function of the basic statement is that we now have a generalization of the previous boundary conditions, where instead of 1 of alpha and beta being set to 0 or to a fixed value, they are proportional to each other with some constant proportionality. And we can now figure out, so now we can write it. Now let me again, the j is not interesting, it's just again, it's the generating function, so to keep things simple, we now have, we can now write the mode expansion that phi is alpha z to the, z minus delta plus beta z to the delta. We're in the regime where delta is less than d over 2, so this is the larger mode of the boundary. Sorry, this is the larger mode of the boundary, this is the smaller mode of the boundary. But the point is, if alpha and beta are now both turned on, there's just some constant proportionality between us, so I can make one of these like one in terms of the constant. This is one definite linear combination that these two terms turned on. And the point is now that if you go towards the boundary, this mode dominates. And it looks like the alternate quantization, the one that we started with in the UV to get that range of dimensions. But in the IR, this mode is the one that dominates, and it looks like the usual quantization in which delta, the effectiveness operator, is now changed to the minus delta. So what this is describing is a flow between the two possible boundary conditions for the given bulk mass squared. Is a flow. So we call the alternate quantization that is quantization in which you have an operator whose dimension is in that range. That happens. There are other operators in the N=4 theory, but in many variants of the N=4 theory, you do have operators whose dimensions are in that range. But in fact, as a sort of point of naturalness, that's unnatural because if you turn on the double phase perturbation with even a small coefficient, the system will flow to the other solution where the operator moves up a larger dimension. And this has some relevance to the modulatory liquids, the sun we're talking about, where you have various flows going on in the theory. This example also exhibits another idea that's worth remembering, which is that if you look at say the second line there, the second line, we've taken the original AES CFT theory, and we've added a field sigma that couples to an operator from CFT. This is just an auxiliary field. Its action is just this local sigma squared. But you can imagine generalizing the structure and coupling fields in, whereas in a sigma squared you have some typical Klein-Gordon action or some kind of non-trivial dynamic action. Some you can make any operators have a direct action. And what does this mean? What this means in this case is that your Lagrangian theory has two pieces. It has a strongly coupled piece, and it has another piece which maybe weakly coupled has just a explicit Lagrangian. And the strongly coupled piece has a gravity solution. These two pieces are coupled together through some interaction like that sigma O up there, some bilayer interaction. And so this is kind of semi-holographic, where you have a strongly coupled piece, and you're using gravity to solve the strongly coupled piece, and then you're coupling that solution to an explicit Lagrangian description of the other part of the theory. And again, this semi-holographic idea, it's something in a lot of different places. There's no reason you can't, basically, you're adding fields to the boundary theory by hand, and there's no reason you can't do that in a definite physical meaning, as I just said. And again, it comes up in these two functions that Han is going to talk about. Yes. So in the N=4 theory, that's not invariant under the N=4 theory, so you wouldn't have it. That theory doesn't have this operator, right? So in some cases, if you insist that your starting point preserves supersymmetry, then you don't worry about this. But from kind of a condensatory point of view, you have some UV theory, and you get the most general Lagrangian persistent symmetries, which will usually contain some terms, which means that it's unlikely in this framework to find operators whose dimensions is in that the ultimate range. Well, that can happen at small n. So indeed, and of course the real world n is not so large, and so indeed we're talking about things that happen within this large n universe that indeed may not need to be true at small n. Yeah. But at small n, the distinction between single trace and multi-trace begins to break down. When you get n =1, there's no distinction at all. When you get =2, you got single and double trace, but the triple trace are redundant. So the whole distinction of single trace and multi-trace is sharpest in the 1 over n expansion. Well, I actually assumed that sign to make it attractive there, to make things work out nicely, which is the sign I also got from the references I'm following, doing the notes, Seaver and Schomer and Berkowitz on this. The other sign is left as a homework. I'm not sure what happens. I mean, look, with the other sign, you can plug it on an I in somewhere, and you get some complex metal points, but I'm not sure if there's any significance to that. Yeah. Okay, actually, look, one second. I'm not sure what happens, actually. It's certainly, obviously, so the sign really saying that, the sign makes a big qualitative difference. Because, and actually, it's an interesting question how cases come to begin. There's something, I think, potentially to show that here, mainly, if you make Joseph more complicated, also level action for sigma, and so integral, yes, you would have gotten some complicated power series in other words, the right line, not normalized there, which doesn't look like it makes sense. But this analysis seems to, well, suggest that you could make it different. The way I set things up, I never actually had to regulate the theory by putting in, by cutting off supergravity theory at some scale epsilon. But if I start writing down things that have non-normalizable bits, I have to regulate it, and all those non-normalizable things probably not be irrelevant. But yeah, I mean, normally there isn't. You go down dimensions where O2 goes important, so on irrelevant. What if I do this trick? Then I wasn't in this range, so O2 is irrelevant. Okay, then if you do things carefully, you will find that if I put a cutoff, you'll find the inverse obviously stable. Right. Okay, so those are the two biggest subjects, are the only ones that really have a lot of equations with them. I mentioned orbitals and covered the main points. I just wanted to make a couple more points. We're going in the direction of small perturbations of the theory, not the large ones, but not so large. Overfolding is a fairly conventional way to write on a theory. So if we have the 6 directions that are transverse to the free branes, and if we divide by some, we identify under some subgroup of rotation group, then the origin becomes a singularity, but in a simple way, and the method of images, you know how this works. And so on the supergravity side, on the EDS side, we just taken S5 to S5 mod gamma, and on the CFD, you got some sort of equivariation theory. Teaching, with ZK, you get, if gamma is ZK, you get, first of all, you get US to the K in the gauge group, and then you get various bifundamental matter charges in different sectors, and the details of the matter depend on, there's different ways for ZK, the ZK can act on the physical coordinates and on the fermions, and so you get different kinds of fundamental matter coupled into this group with n equals 2, n equals 1, and as Tom says, n equals 0 supersymmetry. Tom mentioned that in the n equals 0 case, as far as anyone knows, there are no conformal theories of weak couplings, right? That, you have the weak coupling data functions, right? I was reading your session, I thought you were talking about what the data functions of the theory do, which is the perturbative data function. No, not in this. There are double phase operators. What happens to weak couplings, there are double phase operators everywhere. I actually want to provide the strong coupling counterpoint to that. So, in the case of, again, the amount of supersymmetry can be 2, 1, or 0. In the case of no supersymmetry, you always worry about instabilities, and I want to tell you what they are. So, in the first place, if some non-supersymmetric rotation, some supersymmetric rotation has a fixed point on the phi sphere, there's going to be some tachyon, and the theory will instantly be unstable. What happens generally with these localized tachyons is that some kind of hole forms in the space, and it gets bigger and bigger very fast, and your whole space goes away. You have no gravity side, you also have no gauge theory side. This is the general sickness that non-supersymmetric field theories from coupling are typically unstable. Even when, in a non-supersymmetric case, even when you have no tachyons, even when there are no fixed points of the non-supersymmetric elements, you have the same process non-perturbatively. It's just Witten's decay to nothing, where this hole here is not due to a tachyon rolling down potential, but due to some tunneling process where the whole space tunnels from its original shape to this one, develops a hole, and then grows. So an example is the general phenomenon that the non-supersymmetric theories are unstable. In this case, if you're willing to deal with metastability, and there's no reason that you shouldn't be, by putting some kind of UV cutoff on this space, you can, in the case that it's a tunneling instability, you can make the theory hang around for a long time, and ignore it, talk about duality. Okay, this is what I want to say about overfold. I want to sort of keep the rest of the story of the non-supersymmetric case. Yes? I want to say yes. The difficulty with overfolds is that they don't, if you have, in the large end limit, this is inheritance. And so you basically take, and so in general, in the leading large end limit, anything that happens descends to the overfold theory. If you have something that depends on the next order direction, then not necessarily. Yeah. Also, unless you overfold, you have new possibilities because there are operators in the Swift sectors which didn't exist before. So that's your new possibility. It doesn't destroy the original solution yet. So one can build new examples by combining RG flows and overfolds. For the supersymmetric overfold, you have new operators sitting at the fixed points, and some of them are relevant, and you can imagine turning them on, and now you have a singularity, it can be a whole ring of singularities, and the phi sphere can turn into something like S3 cross S2. So you really can start getting into new topologies. And that's what the counterfold is, and by carrying this, again, it takes some cleverness and some insight about the gauge theory side of duality to figure out where the flow goes to. There are people who have figured this out. And this is a special case of a much more general thing, which is that the field theory is that on the gravity side, you can replace the S5 with any space, which is an Einstein space, in which the Ricci tensor is some constant, positive constant times the metric, and you still get a solution to Einstein equation with just 5 more groups. Actually, once you get into other fluxes like the 3 points we talked about before, you have more general shape. But if you simply just be reading having the 85 theory, the 5 more plus the metric, then you can replace the Einstein space. And if you want supersymmetry, then there's one more condition. It has to be Einstein-Sasaki space, which means that in addition to being Einstein, it has to be Sasaki. Sorry, yeah, not my strong point, but anyway, I need something like that. So that what Michael said is the full 6-dimensional space coming over it has to be classical, yeah. That's the issue, but also kill. It also means that the space has a circle in it, it's not really a circle, right? Anyway, if I give you that space, and tell you, and you have to give me the gauge theory, there's no obvious machine to do that. And what machine one has is this sort of idea of using the combinations of renormalization group flows, overfolding, going out of the Coulomb branch. And so there's a fairly large industry of figuring out the dictionary, which is most complete in the toric case, where there's a cube symmetry of the space. But in the more general case, where there's not so much symmetry, there aren't so many tools. Okay. So working pretty well. So the next item on my list was non-conformal brains. So what if we had started the whole story, what if we tried to repeat the whole story, not with a D3 brain, but with a D2 brain? So with a D2 brain, we get the same gauge theory reduced to 2 + 1 dimensions. And in 2 + 1 dimensions, it's no longer conformal, it's now supernormalizable. If we get high energy, it's going at low energy. And so what we can see is that, well, in And t equals 3 J, we vary the coupling, and in one regime we have the gauge description, in the other regime we have the gravity description here. The energy itself varies the coupling force. At high energy we have the gauge series is the z direction, which means the energy runs this way. I really don't like that. I really like energy running the other way, but everybody starts to use C, so you gotta use it anyway. Okay. And so at high energy you have the gauge theory. That's a good description. Now what happens in the bulk is, on the other side is you have the D2 brane geometry. And so it's the same kind of story, but again, just with respect to energy, that is the high energy part. So in the gauge theory, high energy is effectively perturbative. As you reduce the energy, it becomes slowly coupled. On the geometric side, you have some range of scales where the geometry is good, and as you go to higher energy, it breaks down the same way the D3 brane theory did. That is, the curvature becomes large compared to the string scale and can no longer be trusted. So when the curvature becomes large in string units, the gauge theory description is a good one. In this case, there's another fun thing that happens though, because in addition to the curvature of the dilaton, which was constant in the D3 brane solution, the dilaton blows up. Okay, the dilaton blows up as you go to larger Z, which is lower energy still. And again, that's not a surprise. The D3 gauge theory, again, the coupling is growing at low energy, and that's reflected in growth of the dilaton. But at some point, the dilaton becomes large, and we can no longer use the 2A string theory to describe things, and we have to lift the M theory, and the D2 geometry eventually goes over to the M2 geometry. And so this provides one Lagrangian description of the M2 branes. In recent years, other ways the flows of the M2 branes have been discovered, but it's just the same gauge theory that we've been talking about, but in one less dimension. In one less dimension, you might think that it confines, because gauge theories in 3 dimensions really want to confine, because of the supersymmetry it can't, and instead, as you go to very low energies, the coupling is very strong, it gives you a realization of the dual to the M2 branes. You can repeat this for lower dimensional branes and higher dimensional. Say, as you go to lower dimensions, you get infrared fluctuations and things get more complicated. But I want to say there's a good comment here to correct me, but one of the things we can do at this level, we could have taken the D3 branes and compactified one spatial direction. Make it periodic. And if you think about that on the gauge theory side, the lower physics should be now one less dimension. It should be this is 4 dimensional, it should be 3 dimensional. So when you put on the gauge theory side, if we compactify one spatial direction, we should flow to this story at low energy. And indeed on the gravity side, because of the way the metric is taking off at large Z, the direction that's identified becomes smaller and smaller. You need the T dual, and so you get to the D2 vector. So when I discovered the different dimensions fit together under capacitation and T duality. You can now do this in 2 more dimensions and take the D3s down to D0s. And I think it's fair to say that the Banks et al. Matrix theory in this way is implied by the ADS-CF duality to 3 tons. Yeah. Not really. You never agree. Okay. It's hard to see this derived from this as a larger theory. Doesn't follow. Yeah, I think when it's derived, one makes assumption. One assumption is simply the value of capacitation, which is a pretty safe one, but pretty self-right, right? So, and also you could go in the other direction. I think it's harder to argue that ADS-CFT follows from Matrix theory because there you're looking at extremely low energy vector of the D0 brane quantum mechanics, doesn't capture the supergravity regime. But what's clear is that these 2 things are cousins of each other. They're not identical. Neither may be fully contained in the other, but they're very close cousins of each other. Okay. You can also go up to D4 branes and higher, and I don't want to belabor the point, but you sort of get the same flow in the opposite direction. Just reverse these arrows. And the gauge theory describes in that case the infinite physics because it's not normalizable, and as you go to higher energy, you flow to the D4 geometry, and eventually to the M5 geometry. Anyway. Okay. You're being a very good audience today, or can let you go finish. Okay, so turning more to things that, might be useful in everything in their own right. Oh, I want to say one more thing about the 2+1 gauge theory, which I harp on the fact that ADS-CF duality is a non-perturbative definition of quantum gravity. And, if you're a stickler, you might say, well, do we really have a good non-perturbative definition of the storm theory is strong coupling? You put a lattice, but it's strongly coupled, you don't have good control of the continuum limit. So in fact, when I make that statement, I always have in the back of my mind the T equals 3 gauge theory, which is super normalizable, which means that you can put it on a lattice, preserving gauge invariance, goes into that, but without regard for supersymmetry. Because it's normalizable, you can really analytically control how the supersymmetry returns in the continuum limit because everything's getting weak and you have analytic control of that limit. So that's the other reason I like to try out the D2 brane version of the duality. Okay, now, D2s and D6s. So, you can start getting more branes in different directions. And again, I'm focusing on some of their kind of interesting maybe sort of condensed matter connection. So, there's a lot of conformal field theories, even non-supersymmetric conformal field theories in 2+1 dimensions. Suppose you have, basically that's the, so what loop? I want to write the RG equation not for the gauge coupling itself, but for the effective dimensionless coupling, which is that divided by the scale, and equal to gamma. And then you have mu partial mu gamma squared is minus gamma squared plus phi naught gamma to the 4th. And so this is just dimensional. This is just saying as you go to high, this is now again 2+1 dimensions, C equals 3. And so as you go to higher dimensions, gauge couplings get stronger. As you go to lower dimensions, higher dimensions get weaker, lower dimensions get smaller, stronger. And now you have a one loop term. And I want to play the game pretending that the one loop term is the only one that matters. And so if V naught is positive, there's a zero at finite gamma. And in fact, as you go to lower energies, gamma stops getting strong and flows to a non-trivial IR fixed point. In many cases, that's how universal it is. I think you can think of V naught as being the same data function that you would have had for this matter content D equals 4. And so in particular, we're talking about positive V naught. And so if you have a gauge theory which is infrared free in D equals 4 and reduced to D equals 3, then you get this non-trivial IR fixed point where the dimensional growth of the coupling is balanced by the quantum suppression of it, quantum screening of it. That's the indication where everything I just told you was reliable. If you take, so you have some gauge theory, take a large number of matter fields. So this is vector large N, just n copies. Then we know that the one beta function becomes more and more dominant in the large N limit. The one terminal survives, and this argument is reliable and gives you weakly coupled fixed points. What happens as you reduce n to the f, and you get strong, you get to potentially stronger one coupled fixed points is less clear and depends on a case-by-case basis. But now we can make a dual version of this story by taking D2 branes lying within D2 branes lying within D6 branes. So the intersection is two-dimensional. Now you have the D2 brane gauge theory, which is a highly supersymmetric thing, and you have additional matter from the 2 6 strings. And the D2 brane theory by itself gives a total contribution of 0 to this, because the data function is 0 due to the high degree of supersymmetry, and then the D6 branes make a positive contribution. And so when the number of 6 branes is much greater than the number of 2 branes, you have a weakly coupled fixed point. In this case, there's enough supersymmetry to guarantee that this survives as you take more 2 branes or less 6 branes and reverse the inequality. And also in this case, you can actually write down the metric of the dual theory. Normally when you have branes of different dimensions that are localized within each other or when they're fully localized and not smeared, you can't. But here you can secretly use the fact that when you lift the D6 brane to M theory, it becomes an orbital fixed point. Which was given in earlier homework problem. And again, this is a nice starting point for discussing various phase transitions in these two-dimensional gauge theories. And by the way, there's a regime where this looks like a 2A solution, and there's a regime where it looks like an M theory solution. And it's very similar, actually, to the ABJM story. It's almost all of the ABJM story, but it's similar to that aspect of the ABJM story for a different orbifold of the M2 brane. Now, the reason I'm talking about this is because I told you that I want to make a Fermi liquid. And so, the next natural step would be to turn on a chemical potential and make a density of these 2 6 strings. But in this case, because of the supersymmetry, there's both bosons and fermions there. And when you turn on a chemical potential, you generally expect that most of the charge will go to bosons because the exclusion principle lets them all get at their lowest energy state, so you won't get a few fermions. And so I didn't think I could get to this list item. The last thing I'll probably talk about today is simply to replace the D2 brane with the D8 brane, where this part of the story still goes through, and this part of the story still goes through, but you're less sure about what happens to strong coupling because now there's no supersymmetry. I think no supersymmetry is good for one reason. Where the strings have codimension 6, the branes have codimension 6. The strings that stretch between them are all fermionic. And this would seem to be a nice starting point for building a Fermi liquid. You take this brane configuration, take its gravity dual, turn on a chemical potential, let the gravity tell you what happens when you have a density of fermions in 2 plus 1 dimensions coupled to a strong, in this case, non-abelian gauge field. It's a question a lot of one would like very much to know the answer to. So far, there are a number of problems which keep one from this. So this is the best so far top-down construction of Fermi liquid. And recognizing I don't think any of the later seekers will, so it hasn't been especially successful so far. There are lots of instabilities. The D2 branes can repel each other along the Coulomb branch. The D2 branes can repel the D8, which actually has a nice interpretation of chiral symmetry breaking. It just means that some fermion bilinear has got an expectation value. Also, the spherical space, the D6 sphere that surrounds the D2 branes can have modes that are actually BF tachyons. But because there's no supersymmetry, what one in many cases finds is that shape modes of the 6th sphere are unstable. It just runs off to something you don't know where. That's really annoying because the shape modes of the 6th sphere correspond to scalar operators, as we've seen. And you don't care about the scalars at all. They're artifacts that come along with duality and argument system that you care about it. So it's just one of the annoyances of trying to make a top-down construction. Presumably it's possible to stabilize all these things if you work hard enough. And so let's pretend that the system is stable and try to carry out this exercise of turning on. So again, you want to turn on a potential for the gauge field on the D8 brane, that's a chemical potential for the fermionic strings that will take a density form. And so at least the effect would be that you would have a 2 plus 1 dimensional gauge theory coupled to a density of fermions. In the brane picture, you turn on some kind of electric field that runs from the boundary of the space along the D8 brane down to the horizon. And a nice result by Cauchy and Parnichev, which says as you can see now, look at fluctuations of the D8 brane around this, look at the 2-point function, and it looks a little bit like you've got a Fermi surface, in the sense that there are states at omega goes to 0 with finite momentum. And if you think about that, that's not something we ever see in a relativistic system. In a relativistic system, of course, omega is always greater than or equal to k. But a Fermi liquid has this distinctive behavior that we can, here's our Fermi C, and we can take a Fermion out from here and move it over here. And that has very low cost in energy because we just moved it this far in the radial direction. it's changed the momentum by a huge amount. And so there's some evidence that this picture knows about this picture, and so one is really building maybe a fair machine. The problem is that the field line is not obviously really splitting together. The field is growing, it's getting very large near the horizon, and its calculation really isn't self-consistent.